All right, let's talk about the single most important force in the universe. It's completely invisible, but it dictates absolutely everything, from why you're not floating out of your chair right now to why entire galaxies hold together. We are talking, of course, about gravity.
So, let's kick things off with a classic question, the one that supposedly started it all. It seems almost too simple, right? But the answer, first figured out by Isaac Newton, is what connects a tiny piece of fruit here on Earth to the massive planets wheeling through the cosmos.
And this leads us right to Newton's monumental idea. He had this incredible realization that the force yanking an apple off a branch is the exact same force that's holding the moon in a constant dance around the Earth. They weren't two separate things at all. It was one single universal pull.
So what is this law really? Well, at its core, it's actually super simple. It just says that any two things that have mass, and I mean anything, you, your phone, the Earth, the sun, are constantly pulling on each other. It's not just an Earth thing, it's a rule for the entire universe.
So how does this actually work? Well, it really boils down to two simple rules. First, the more stuff, or mass, an object has, the stronger its pull. That's why we're stuck to the Earth and not to the person next to us. The second rule is the really mind-bending one. The force gets weaker with distance, and not just a little weaker, a lot weaker. If you double the distance between two objects, the gravitational force between them drops to just 1/4 of what it was.
And the amazing thing is, all of that, the masses, the distance, all of it can be wrapped up in one elegant little equation that lets us calculate that force perfectly. Okay, so this is a universal force, but what does that actually mean for us right here on the ground? Well, that's where we get to the idea of gravitational acceleration, which scientists just call g.
Here on Earth, g has an average value of 9.81 meters per second squared, and that number is basically the rate at which things speed up when you drop them. It's gravity's signature, the reason a dropped ball doesn't just fall, it accelerates.
Now, you'd probably think that number the same no matter where you are on the planet, right? I mean, gravity is gravity. But is it really?
Turns out, nope. And the reason is kinda cool. The Earth isn't a perfect ball. It's a little bit squished. It bulges at the equator. That means if you're standing on the equator, you're actually a little farther from the center of the Earth than if you were at the North or South Pole. And because of that law we just talked about, more distance means less force, gravity is just a tiny bit weaker at the equator.
Okay, so we've talked about things falling down, but what if you could just keep falling forever? Sounds like a paradox, but that's the beautiful secret behind what an orbit really is.
Newton actually thought about this way back when. He had this great thought experiment. Imagine a cannon on a super tall mountain. You fire a cannonball, it flies a bit, and then gravity pulls it down. Fire it faster, it goes farther before it hits the ground. But what if you could fire it so fast that as it falls, the Earth curves away underneath it at the exact same rate? It would never land. It would just keep falling forever. That's an orbit.
Think about it like this. If you swing a ball on a string, what stops it from flying off in a straight line? The string, right? It's constantly pulling the ball inward toward the center. In physics, that inward pull has a name, centripetal force.
And here is where it all clicks together. For a satellite, or the moon, or anything in orbit, there is no string. Gravity is the string. It's Earth's gravitational pull that acts as the perfect centripetal force, constantly tugging on the satellite, bending its path into that state of continuous freefall we call an orbit.
Now, Newton gave us the why of all this, but funnily enough, an astronomer named Johannes Kepler had already figured out the how decades earlier. He basically laid out the 3 cosmic rules of the road for everything in our solar system.
And his 3 laws are just brilliant. First, he realized orbits aren't perfect circles, they're actually ovals, or ellipses. Second, planets hit the gas when they get close to the sun in their orbit and then ease off the pedal when they're far away. And third, and this is a big one, the farther out a planet is, the ridiculously longer it takes to make one trip around the sun. And you can really see that third law in action when you just look at the numbers. We take 1 year to go around. Mars, our next-door neighbor, takes almost 2. Jupiter takes a whopping 11.9 years. And by the time you get out to Saturn, you're looking at nearly 30 of our years for it to go around the sun just once. That distance makes a huge, huge difference.
Okay, so we've got these cosmic rules. How do we actually use them? Let's bring it back home and talk about the technology we've built and the incredible challenge of actually leaving Earth behind.
When it comes to the satellites we put up there, they mostly fall into two camps. You've got your geostationary satellites. They're in this absolute sweet spot of an orbit where they take exactly 24 hours to go around the Earth. That means, from our perspective, they look like they're just hanging out over one spot, which is awesome for communications. Then you have the non-geostationary kind. They're in all sorts of different orbits, which lets them cruise over the entire globe, making them perfect for stuff like GPS and watching the weather.
But orbiting is one thing. What if you want to break up with Earth's gravity for good? Just leave. Well, for that, you can't just go fast. You have to go fast enough. You have to hit a very specific speed limit called escape velocity.
And on Earth, that speed is just insane. It's 11.2 kilometers every single second. Not per hour, per second. It takes a mind-boggling amount of energy for a rocket to fight against gravity and reach that kind of speed.
Now, just for a little bit of perspective, think about the air you're breathing. The tiny molecules of nitrogen and oxygen in our atmosphere, they're constantly buzzing around at about 0.5 kilometer per second.
And that's the whole point, isn't it? 0.5 kilometer per second is nowhere near the 11.2 they'd need to break free. Earth's gravity has them totally locked down. In a very real way, that high escape velocity is the only reason we have an atmosphere at all.
So you see, it all connects. That falling apple, the orbit of the moon, the satellites in our sky, even the air we breathe. Gravity is this fundamental force that literally holds our world together. But the amazing thing is, once we understood its rules, it didn't just hold us down, it showed us the way up. The only question now is, where will that understanding take us next?